So I was just presenting myself. So I come from University of Naples. Good afternoon to everybody. And I will give you some details of one of the possible strategy we have for introducing reinforcement into 3D printed structural elements. I will give you some details about the technology, the design, and also the weaknesses on which we are currently working as research activities. Everybody has talked before about the need for reinforcement because we know that this is normally combined with concrete, especially in particular areas, for instance, in Italy where seismicity is high, where there is a need for tensile resistant materials, but also ductile materials. So when dealing with this issue for 3D printing activities, we need to change this paradigm because in conventional reinforcement we have that steel is computed, is detailed, and then is placed over a given position, and afterwards a relatively low viscosity concrete is poured and covers the entire reinforcement. In 3D printing, especially for layered extrusion, this situation is completely different because the concrete has a higher viscosity and the bond. So these important characteristics of reinforced concrete may change a lot, as this picture showed in a recent study on using conventional reinforcement in layered extrusion. A recent review have also highlighted which are the possibility to include reinforcement into digital fabrication with concrete. So we can adopt a particular structural principle, for instance, using fibers inside the printing mortar, but also we can place conventional reinforcement inside the object during or before the manufacturing, but also we can think about removing whatever is the reinforcement by dealing with compression loaded structures or making a hybrid solution with the previous combinations. Of course, the strategy is influenced by the technology that is adopted, the equipment which is used, and everything should be connected in order to design and obtain an effective structural element. Here are some examples that are included in the previous classification, so by structural element or by stage during the printing process. So many of these have been shown by the colleagues from ATH, but also other examples include entraining devices for introducing steel cables into concrete layers and also fibers. How much these strategies are effective needs to be demonstrated by testings, and for many of them these tests have been conducted and the effectiveness was demonstrated. Our approach, so the approach that we have explored at University of Naples is basically considered for unidirectional structural elements, for instance beams, so not for walls or whatever, and is considered for the combination with an external reinforcing systems, but for exploiting the possibility of considering very complex shapes along the beam axis, but also to provide some insights for assemble the beam on site and produce off-site the components. The idea is to start from curved longitudinal structural elements or with a variable cross-section along the beam axis, and then ideally cut this beam into several segments depending on the capability of the printer and of the equipment. After printing, these segments are assembled together with a number of external reinforcing systems that is made of threaded rebars connected to some holes which cross the concrete segment, or these segments can be put together with an external post-tensioning scheme. How to think about how to design each segment of the structural element. So we have several strategies, but we can start from conventional structural engineering concepts. So starting from a simply supported beam, for instance, with constant 8, we know that every segment considered is in equilibrium in terms of bending moment and shear with the previous and the subsequent. So starting from this concept, we know that there are some very well established models, for instance, the strut and time model, in which we have concrete strut that are linked to the steel tie made of stirrups together. And normally, if we look at this scheme, this resisting scheme under bending loads, we can see that most of the material can be removed, and the mechanism can still act against the bending moment. And this was the first try that we have attempted at our lab. So we wanted to print a strut and tie model using a concrete printer. So we have at the beginning, in the first step, divided a 3-meter long beam into 7 different segments, in which we have designed the concrete strut and the tensile and compressed cord of the entire beam. These segments are then combined with an external reinforced configuration made of threaded rods, which are then glued and fixed according considering a low viscosity mortar in the holes that were previously printed using a particular equipment. At the interface, we have used the same flowable mortar to guarantee the connection and continuity among the different segments. And in the holes, we can see here that some longitudinal rebars are also connected to the tensile ties, which are linked to the compressed cord and the tensile side of the beam. Here are some details of the stages to produce these structural elements. On the left, you will see one of our first printer that it's made of basically a printing head that is an extruder and three moving braces in an area of 3 meters by 3 meters, but this has been changed with the new one that I will show later. And each segment is made of segments of 60 centimeters of length, 45 centimeters of height, and a single or double path depending on the need for the concrete strut in the structural scheme. Here are some details of the external reinforcing system. There are some hexagonal nut rod pipe that allows also to measure the tension inside and control the tension inside each rod. And as you can see here, there is an out-of-plane rebar system that connects the two external reinforcing systems, and everything is locked here with male thread connectors, and this out-of-plane rebar system is fixed to the concrete segment by filling the hole with a cementitious mortar, a flowable cementitious mortar. Here is the test that we have performed by combining and assembling this type of structural element. The 3 meter long beam was tested in a simply supported scheme in 3-point bending test at our lab at University of Naples. And the goal of this test was to analyze the failure modes, but also to see if with this strategy, a design ultimate bending moment could be achieved with this technique. Here is the result in terms of flexural load versus deflection. We see here that the trend is not continuous because there are some drops in the curve, because the beam starts with a linear elastic behavior up to flexural cracks in the bottom side of the beam, but afterwards the stiffness changes, and also further drops appear because there are some cracks inside the connection and the anchorages. What happens at failure is that one of the elements rotated, and a complete interface failure was achieved between the second and the third element. And this is mostly a local stress concentration around the connections and at the interfaces between the elements. We have also investigated and explored this result in terms of finite element interpretations, and actually we have reproduced these flexural stiffness trends after the drops by removing the connection at the interfaces at the anchoring holes. So looking at the overall results, we can say that with these strategies, or with the external steel reinforcement, before any crack appear in the beam, we can achieve an intermediate flexural stiffness if compared to an equivalent solid one with the same cross section but solid. So intermediate, I mean between a full solid and a cracked beam with the same cross section. So before the tensile crack appears, we are in the middle of these two possible trends of an equivalent solid beam. For this type of example, the local mechanisms have a significant effect on the overall behavior of the beam. So in fact, we did not achieve the ultimate bending moment, the design ultimate bending moment, because there was no yielding of the steel due to the premature failure of the anchoring and the interfaces. An interesting result is that we used more or less the half of the concrete adopted for an equivalent solid beam, and the same approach could be used also for freeform profiles. So, and this was the second example that I want to show you. So, considering this approach, instead of having a straight beam, we have tried to draw an external and internal profile of a 4-meter long beam. The profile is the one of the volcano Vesuvio that is behind Naples. And we have designed as the same external reinforcing system, so made of threaded rod and combined with an out-of-plane and in-plane reinforcing system. The computation of the ultimate bending moment was made using finite elements because the shape was not regular, and this kind of analysis was also conducted to consider local effects that were experienced in the straight beam. And here some further analysis related to the contact pressure in the compressed zone, because here the layers are oriented along the bending direction, and if too much compression accumulates at these interfaces, we can experience the expansion of the layer in the transverse direction. But I will come back on this issue later on. And here some details of the processes. So once all the segments have been printed, they are placed on a support, and external fixing is made through the out-of-plane and in-plane reinforcing rebar. And here is the final result. The final result has the profile of the Vesuvius volcano, and here after curing, we had the external side of the reinforcement that acted on both sides of the beam. Well, what I've learned here from these experiences, if we want to keep on working on this strategy, so the external one, we have to say that the dimensions of the printed element has a huge effects on the results, because it may lead to stress concentrations at the interfaces. So one possibility is to avoid the division into segments and try to print the entire beam without any interface. And this is what we are doing now with the new printing equipment. And the same for the straight beam. Second lesson was related to the direction of the layers that work under flexural loads, because in the compressed side of the beam we had the concrete layer were subjected to compressor load along the direction of the concrete layers, and this was a little bit different of other application in which concrete is loaded in the perpendicular direction of the layers. So in our case, we should be care about the possible expansion in the transverse direction, and to work on this issue, we are considering an external post-tension steel system that is able to contain this expansion. Further lessons, okay, is that stress concentration can be very high and can reduce the the bending capacity of the beam. So many improvements can be done in this direction. So first of all, we can improve through the thickness strength of the beam to avoid the failure in the interlayers, in the weak interlayers. But as well, we are adding much more points in which the external system is attached to the concrete structure in order to reduce the stress acting on a single hole, on a single attaching site. A further point that came out is to promote, to introduce an alternative way to combine the printed concrete with the classical reinforcement, and this is what we are trying to do with the lost form work approach. So combining a freeform profile with a conventional steel cage, but at the same time providing some functional voids and introducing new functionalities to the beams. And fifth point to improve this technique is to change the resisting mechanical optimization scheme, because that strut and tie scheme resisting mechanism is common and is very effective for conventional reinforced concrete. So we are trying to change this approach by focusing more on topology optimization methods, looking also at the printing constraint. All these novelties, all these improvements are currently ongoing at our lab in Naples, in which we adopt a robotic system combined with a continuous pumping concrete feed. And here, just to give some examples of the activities which are still running. So this one is related to the change of the optimization scheme. So no longer the strut and tie model, but the topology optimization scheme, which is also optimized using printing constraints. For instance, in the first picture, we see an optimization without the printing constraint, and sometimes this can give rise to some paths that cannot be printed. For instance, some crossed lines that should be avoided when considering printing. And here instead we have included printing constraint, and we have avoided some not feasible printing paths. This last one is related to the lost formwork scheme to try to exploit conventional steel cages. So we define a profile of the beam and remove virtually the material that we don't need inside, and afterwards we place reinforcing steel in it and cover it with conventional poured concrete. So these are some of the improvements that we are doing. But in conclusion, we can say that this approach is promising because it can allow for a reduction of material consumption and also provide the possibility of producing structural element, in particular beams, with freeform profiles, but at the same time, much work should be done in terms of connections to avoid local failures. But promising results are ongoing if we change the resisting mechanism in under flex roll loads, but also improving the connection systems with more attachment to the existing RC printed elements. So I would like to thank you very much for your attention, and thanks again to Eric and Liberato for inviting me to this session.